it's great to be here, and it's nice not having an all-grade screen, which you was doing before, so that's good. So I'm going to tell you a little bit of astrophysics from an applied mathematician, fluid dynamicist point of view. So I want to tell you about, first of all, what the words in this title mean. So let me start at the beginning with the word. Okay. So protoplanetary disks are disks of hydrogen gas around not stars, but protostars. Stars that are almost there. They don't have enough mass on them to start nuclear burning. Okay, because what happened is it started with a big, huge shell of fluid, and it collapsed, its cores collapsed, but because there's angular momentum typically in these things, they don't uniformly contract. They understand where the axis of rotation is, and they become kind of disks. And the angular momentum axis is perpendicular to the disk they fall on. Okay, and then the gas goes into orbit, and it goes, and it's very cold, so there's not much pressure support. So the support is between the centrifugal force of the gas going around and the gravitational pull of the protostar, and so you get Kepler's laws. So you get these Keplerian disks. And you can see these through the Hubble Space Telescope. If you're looking at a disk face on, the bright spot, you're looking at the protostar. Around it, you're seeing darkness, which is the dust and the gas is blocking the light from coming out. If you look at these guys edge on, you see that there's a big dust band across here where you don't see the light, and then above and below the disk, dust, you see a disk of light, and so the protoplanetary disk is in here somewhere. 500 AU is the typical size in these pictures. An AU is an astronomical unit, the distance between the Earth and the Sun. So that's what a protoplanetary disk is.
Can I ask a question?
Yeah.
Which is, bottom left, we're seeing a disk which is in shadow because it's being blocked by the dust. But the light has a particular circuit, so it's reflecting off something.
It's streaming out from the sky. So there's this star, almost star, there's light going on here, and you don't see it because it's just blocked. And so you're seeing here where it becomes optically thin through the dust, so that I can see it. And then there's also, it's beaming out, as many of the secreting objects do, along its axis of rotation. Okay.
So reflecting off the lighter dust, that's what we see.
You mean scattering?
Scattering off.
It comes scattering off dust or gas or whatever. Yes.
More optically transparent.
Correct.
Later.
Correct.
Okay.
So these protostars need to become stars, right? Otherwise there's no origins. And the dust needs to somehow get together. The dust is somewhere between 100 microns, maybe 100 centimeters. It's got to accumulate together, and then it's got to agglomerate, stick together, so that it can become big enough and overcome the random velocities, and then it becomes big enough. It's a magical mass or a magical radius of about kilometers to hundreds of kilometers, and then you get runaway gravitation. You get planetesimals and planets, and you and I are here. But there's a problem. Okay, with this. Okay, the problem is that there's a dead zone. So all astronomers like to talk about colorful things. So the dead zone is what they name this region from about 1 AU in radius to maybe 10 to 50 AU away from that central protostar. And the problem is that you've got this gas, and it's in Keplerian orbit, and it's got to get out of orbit to fall onto the star. You've got to destabilize it. You need something to rob it of its angular momentum and energy. Otherwise, it can't fall in. Furthermore, this dust is out there, and it's not going to do anything in terms of accumulating or agglomerating unless there's some instability, typically because these vortices, as you'll see on here, the vortices are not like the ones you've got in your bathtub. They're like the ones on your weather map that are labeled highs. They have high pressures in the centers rather than low. In a low pressure center vortex, if you have heavy objects, they will centrifuge out. But if you have a high-pressure center at the center, then they centrifuge in. And that's a great way of accumulating and attracting dust to make planetesimals. Okay, the problem is that we don't know of any stabilities, because the argument ever since Rayleigh has been that if you have a fluid, and the magic words are constant density, and the angular momentum per unit mass, if it decreases as you go inward, which would be the case for Keplerian orbits, then you're going to be stable to all kinds of stabilities, linear instabilities, finite amplitude instabilities, whatever. And so this is a problem. People had thought that the problem was solved when Steve Balbus and others rediscovered a magnetic resonance instability that was discovered, had previously been discovered and then forgotten by Chandrasekhar, who previously discovered it from the old Soviet scientists. Right? But they thought that, this instability that couples fluids with magnetic fields, it's perfect for this. It's got a fast time scale, transports angular momentum, problem solved. Problem is solved for high energy disks around stars like neutron stars or black holes. But these guys, these protoplanetary disks, have temperatures from about 50 to maybe 100 degrees absolute. With those kinds of temperatures, you do not ionize. You have neutral particles. You can have all the magnetic fields you want. You're not going to have any coupling between them. So this instability that everybody loves will not work if you have a cold disk. And this problem was realized about 15 years ago. So people have been looking for a purely hydrodynamic fluid instability to destabilize these disks. So I said, well, you need these kind of retro rockets to think of angular momentum. All right.
Can I ask a question?
Sure.
What's the mean free path of the dust? How much does
the dust, if I were to take, I can't say football stadium, if I were to take a soccer stadium, right, basically, and look at it, right, and it would have maybe 4 dust particles in it.
Well, very
but there's not a whole lot of dust. Okay. Okay, so again, Lord Rayleigh, right, of fluid dynamics fame and other fame, came up with this theorem, but it actually is a theorem that only applies to constant density fluids, not fluids bound constant density. And people, though, have decided that this must work for compressible gases and other things. There have probably been at least 50 numerical simulations where people start with a flow that's Keplerian in a protoplanetary disk, and they see that it is stable. They whack it, they tweak it, they whatever they want. But there's some problems with those things. Among other things, there's not much resolution in these calculations, and the other things that they have a lot of grid dissipation associated with it. Okay, so here is a typical paper by Steve Albus and others. It was the Astrophysical Journal in 1996, and they plotted, and this is very typical. There must have been a lot of people have reproduced this plot. Here is time in units of local years of takes gas to go around the disk. And on the vertical axis, they plotted the energy, not the total energy, but there's some energy associated with the Keplerian disk velocity. So they superposed noise on that at the beginning, and then that gives you a non-Keplerian component of the energy. And they want to see how that evolves. If it decays, that means the flow is stable, and if it grows, then it means the flow is unstable. So they've done a bunch of experiments with angular velocity, capital omega, as a function of cylindrical radius r, where r goes to some minus q power. So for a Keplerian disk, that value of q would be 1.5. For the angular momentum to decrease as you go out radially and be unstable according to Lord Rayleigh, q would be 2 or greater. So here it is. Lord Rayleigh is proved by initial value calculation. You start out with some noise, and the noise always decays, especially for good old Kepler. But if you're greater than what Rayleigh says too, it's unstable, problem solved, case closed. But not quite. So these guys did their calculations with a fully compressible gas, right? Ideal gas law, PV equals nRT. But when they initialized the flow, they did something odd. They initialized it with a constant density of fluid. And so here's my star over here. My star is pulling at things gravitationally in a spherical pattern. And the cylindrical component of that gravity is balanced by centrifugal force, so there's some leftover gravity. So this is my disk. There's gravity going down this way and up this way. Okay, so that gravitational component is not that strong. Moreover, so they decided not to include that. And they said, okay, so a real disk, if you have something like, say, an isothermal disk vertically, it would be very, very dense at the midplane and then fall off as a Gaussian as you went up vertically. So most of the density would be down kind of at the bottom where the disk is. And that would be called stably stratified because it's much denser down below. So the argument was, or so I pieced together, I'm talking to various people, well, we don't have to study flows with variable density that's stably stratified, because we proved if it's not stably stratified, then it's not going to have any instabilities. If we stably stratified, of course it's not going to have any instabilities. And that's just completely wrong. I mean, fluid dynamics is very anti-intuitive. When you make something with constant density, you make it a barotropic fluid rather than a baroclinic fluid. In a barotropic fluid, the surfaces of constant density and the surfaces of constant pressure are all parallel. In a baroclinic fluid, they don't have to be parallel. And that introduces a whole world of instabilities. If you could look outside that window where the blind is closed, if you looked at our weather, almost all of our weather is due to baroclinic instability. So by doing this approximation, simplification, they threw away a world of instabilities. And that would become very, very important. So people already kind of suspected that. You can take fluids without constant density or that are stably stratified, and people have noticed a number of instabilities. There's the stratified rotational instability. But these instabilities have been discovered by a number of people, starting with Jim McWilliams, I believe. But they're very weak, and they often require something like a boundary condition or something that would not be physically relevant to a protoplanetary disk. So people have kind of discounted these things. Of course, most of the flows that we look at aren't necessarily unstable to linear instabilities. Many of them, pipe flows, channel flows, especially flows with shear in them, can be linearly stable, but explosively unstable to finite amplitude instabilities. So even though you calculate all the eigenmodes and all the eigenvalues, and you get no exponentially growing eigenvalues, nonetheless, if you whack these guys hard enough, you could really create a whole bunch of turbulence there. Okay, so those are finite amplitude instabilities. So we've got a suspicion, Joe Pelagio, who was a former graduate student of mine, back in 2005, we decided to do a numerical simulation of a protoplanetary disk. And we wanted to see if we put a vortex, just ad hoc, arbitrarily, into that disk midplane, what would happen to it? Would it go away? Would it grow? Would it gather vortices? We wanted to know what it would do. And we were curious about that because I'd spent 20 years or so before that sort of continuously looking at planetary vortices like Jupiter's red spot. And the ingredients that make a red spot robust and powerful is that it's sitting in a shearing flow where the vortex is rotating in the same direction as the shear. It's sitting in a rapidly rotating system which inhibits a lot of instabilities. And it's in a vertically stratified flow, which also inhibits things and kind of makes it a little bit two-dimensional. And those are all the ingredients that you have in a disk around a star, because you've got the shear, because Kepler's law is not solid body rotation, it has shear. It's obviously rotating, and it is obviously stably stratified if it's got a Gaussian density profile. Okay, so we looked at these things. And what we discovered was really surprising. We put in a vortex, and we did some negative vortices, and they eventually became linearly unstable when you actually calculate the instability associated with those vortices. But what was weird is this thing, before this thing completely died, above and below the vortex, which was starting in the midplane, it populated a disk with vortices, and we didn't understand that. But I was going to show you a picture, actually it's made a little bit later in that study, of a vortex in a stream flow. So this is a shearing flow. So the velocity, background velocity is going like this here, and above it, the velocity is going in the other direction. So it's a shearing flow. And I plotted with color the vorticity in the direction pointed out, because how fast the flow locally rotates the curl velocity. And I've used color. So blue is what we call rotating in the same direction of the shear. And the shear is what we call anticyclonic for a Keplerian disk, because the shear has the opposite sense of rotation as the overall disk. All right. And red is therefore the other side of the vorticity. And this is what we call a shielded vortex. In any layer, it would have no net circulation. And many vortices in nature, for reasons that I won't go into now, would be shielded. So we decided to start with a shielded vortex. And this is a 3D calculation, and you're looking at the midplane of the disk here. So it stops at some point above the disk, it stops at some point below the disk. But what was interesting about this is if you let this thing evolve in time, it kind of falls apart, but it kind of comes back together. It's going to fall apart again lately, but it produces these funny stripes, these bands of vorticity. And first of all, that's got to be numerical. It's got to be something weird going on here. And then these bands, you can see, are rolling up into other vortices themselves. And we didn't quite know what was going on, but it was clear that somehow this thing produced other vortices. And a lot of indications that it had something to do with waves were triggering these new vortices. What kind of internal inertial gravity waves? So where internal waves are when you have a continuous stratification, dense densely stratified, right? So stable stratified flow. You're allowed to have waves on it due to gravity, and you also can have waves due to the restoring force of Coriolis terms, and the combination of that, these inertial gravity waves. Okay. So,
what were the boundary conditions?
Oh, for this guy over here. Okay. So for this guy over here, we've done these calculations with a lot of boundary conditions. In this particular calculation, which was the boundary conditions we used in that 2005 AppJ paper, so this would be this Cartesianized version of an astrophysical disk. So this would be like the azimuthal direction around the disk. This would be the cross-stream direction, which would be like the radial direction, and this would be the vertical direction. So in the streamwise direction, we use what astronomers like to call the shearing box approximation for the boundary conditions, and that is that we're periodic in the streamwise direction. In the cross-stream direction, you go into a frame where you take out the Couette flow velocity and you make the plane shearing velocity, and you make it periodic in that direction. That's just a simple transformation. And then we are in the vertical direction, we're mapped to infinity, plus or minus infinity in this calculation. But we've done it with periodic boundary conditions, we've done it with impermeable boundary conditions. The boundary conditions do not have a very noticeable effect on this problem. Good question. So we looked at this. This was 2005. It's now 2015, and we'll try to figure out what was going on here. And it was very difficult because for a protoplanetary disk, you've got this odd density, this Gaussian density profile. You've got a lot of things going on. So the idea was simplify, simplify, simplify. See if we can find a simpler problem which has the same phenomena in it, and then if we understand the simple problem, go back and try to understand the protoplanetary disk. And so that's what we did. So we went to plane Couette flow, which is the simplest shearing flow. It's going to flow one like this, flow one like that, either bounded or unbounded. So very simple. Take that shear, let me do it this dimension, about sheared one like this. I'm going to take this whole table, and I'm going to rotate the whole thing. So I add then rotating flow. And then I'm going to, in the vertical direction, I've got gravity, and I'm going to have a density profile, not Gaussian, but let's make life simple. Let's make it a linear profile. And a protoplanetary disk, the gravity is also a function of constant gravity. So the simplest things we do, forget using an ideal gas, forget using something, an anelastic approximation, use the simplest approximation that has any density variation in a Boussinesq fluid. So that would describe, say, salt water in the ocean or salt water in a laboratory. So the Boussinesq equations are very simple. Right? The velocity is v. We've got the usual no dissipation here. Euler's equation. We've got a pressure. We've got a mean density rho naught. But I'm in a rotating frame. F is my Coriolis parameter, twice the angular velocity pointing in the z vertical direction. I've got gravity here, and I'm looking at the density effects due to the density minus the mean density rho naught. Boussinesq, so it's divergence free, and the density of the mass just goes with the flow with no kinds of diffusion. Okay, so they're the simplest equations when we do that to see these effects. Is there a question? Great. So here it is. So I can go and study Couette flow. Right? So here's my plane flow, and the velocity is as simple as it could possibly be to stop shearing it. The velocity is a function of cross-stream direction y going in the x direction, and it's got a uniform shear sigma. So we've simplified the heck out of this one. And if you go and you calculate all the eigenmodes of this, you find that everything is neutrally stable. So, right, the eigenmodes, right, they go to either that something t, that something has a real part that is not positive, so it's not growing, it's not negative, it's not decaying, it's zero, so it's neutral. It can have an imaginary part, so the phase speed can be finite, and it can move around any way it wants. But it's neutral, it's not going to do anything. You do the same thing, you include vertical rotation coming around here, Coriolis parameter F equals twice the angular velocity, still calculated, it's neutrally stable. Put in gravity, and now stratification this way. The stratification is parameterized by one number, and one Weissler frequency, which depends upon the gravity, the stratification density, and it has dimensions of 1 over time. Physically, if I take a stably stratified fluid and I perturb it up and down, boom, then it will let go, it will oscillate at that one Weissler frequency. This problem, if I have it unbounded, has no parameters that have length scales to them. It's got 3 parameters, but they're all dimensions of 1 over time. One is the Brent-Weissler frequency. One is the shear, which also, of course, has dimensions of 1 over time. And the Coriolis parameter also has dimensions of 1 over time. For a protoplanetary disk, these numbers are all the same, approximately. Okay, so we want to be in the region where each of those things has the same kind of impact upon the system. I calculate the eigenmodes of this guy, and they're all neutrally stable. Okay, so this guy is not linearly unstable, but it does have critical layers. So critical layers, many of them should be sure what critical layers are, but let me just review it. It used to be taught a lot when, in the olden days, when I was teaching fluid dynamics originally, many, many years ago. And what a critical layer is about, when you have a shear flow, most people are interested in critical layers of shear flow, you sometimes get a critical layer when the unperturbed velocity, V bar is my unperturbed velocity, there may be some location in the fluid, in the cross-stream direction, Y star, where the actual fluid motion matches the phase speed of the eigenmodes moving along there. Right? In that case, you can get at that location, you find that there is a singularity in the flow. In this case, it's a weak logarithmic singularity. Kelvin was really interested in these things and thought they might be easily energized. We call them Kelvin's cat-sized instabilities, and he produced vortices. But it's very, very hard to excite these modes in the laboratory. Very, very hard to excite them in any numerical simulation. So they're not all that important, therefore, in many cases. But this is just a really special fluid dynamics version of a critical layer. So if you go back to sophomore mathematics, when you learned how to solve ordinary differential equations with the method of Frobenius, the first thing they tell you before you do your series is say, you better look for singularities in solutions. So there may be some there. And so look at the coefficient of the highest derivative term in your ODE. If that vanishes at any location within your domain, you can have a singularity. It could be log or it could be worse. Okay. So really the question is, what about the highest coefficient? We found a bunch of new critical layers that hadn't been seen before. And these critical layers depend upon the Brent-Weissler frequency, so they're baroclinic because they depend upon the stratification as opposed to the old-fashioned ones, which I'm calling barotropic because they didn't get really stratified at all. And these are going to be really important because they're going to be really easy to excite. In fact, to not excite them becomes a very difficult task. Okay, so just to put down the math, if I write down ordinary fluid dynamics, Courant flow rotation, I get basically the Rayleigh equation or the Rayleigh-Coyle equation, and the coefficient, second-order ODE equation, which describes the stream function for the perturbations of that flow, and the highest derivative, which is the second derivative, the coefficient in front of it is the unperturbed velocity, as a function of location, minus the phase speed of the eigenmode, so that's why you get critical layers there. Okay, if you typically write things in the usual exponential form, with a wave number x is my streamwise direction, kx is my wave number in that direction. So I can either think of things in terms of a phase speed cs, or in terms of a temporal frequency s, depending upon whether or not I factor the kx out. Okay, but then if I add stratification and I rederive my Rayleigh equation, I see that, this term survives, but there's another term that multiplies. And so it's possible that there's locations where this guy controls the critical layer that forms. It depends upon the Brent-Weissler frequency, the wave number, and the temporal frequency of the wave that I excite. So in fact, the location of that critical layer is given by inverting the velocity over there. But if I have a simple velocity, my velocity is simply linear in y. It's very easy to algebra write down. I can write down by inspection the locations where these critical layers would appear, and they depend upon those frequencies and the wave number. Okay. And these guys are interesting. In the old barotropic case, there is a logarithmic singularity, and you can calculate the eigenmodes. The singularity is always in the streamwise direction. For these critical layers, the velocity eigenmode, the critical, things become singular, is the velocity in the vertical direction parallel to the axis of rotation. That's important because here's the vorticity equation. I take the curl of my governing equation, look at the z component. It's got the usual effect in terms of it. But here's the stretching term. The stretching term has a Coriolis, which is big for a Keplerian disk. It's got the shear, which is big for a Keplerian disk. And it multiplies part partial Vz with respect to Z. Well, Vz is the thing that's going infinite one day in this problem, and so I'm going to produce vortex layers like crazy. All right, and so that is the key to this whole thing. Let me just say that, so I'm going to jump back 10 years and then come back to the present. These critical layers are what we saw in our flow but couldn't recognize them back in 2005. Because if you look at the location of the critical layer, it depends upon the Brunt-Weissler frequency. If you go back to protoplanetary disks, that would be isothermal in the vertical direction. The Brunt-Weissler frequency is linear in Z. Right? If this was constant, the location of the critical layers would be independent of Z, but now, if you go back to the problem actually studied, they'd be linear in Z. And so I can go and back and use ECWK to get that. And let me show you a picture. So here was, we reproduced a picture from what we did 10 years ago. Here's the vertical direction. So Z equals 0 is the midplane. And I've stretched things out to make things visible. This is my cross-stream direction, which would be my radial location, this direction of the protoplanetary disk. And we plopped in ad hoc a vortex at 0, 0. And so this is a vortex whose primary flow, the vorticity is around it, the z-axis. And I'm plotting here the vertical component of the vorticity in black and white. So gray is neutral. Right? It's a shielded vortex, so there's a lot of black in the center, and it's shielded by white. And what now we should have known, but didn't, was this. And this goes on to say, there are waves, inertial gravity waves. This is the primary fundamental critical layer. This is the second critical. They form this X pattern exactly where the calculations that we did. All right. This is done, by the way, with an anelastic rather than a Boussinesq calculation. So it's not, doesn't produce acoustic waves, but the density doesn't have to be constant. This is a Gaussian density in the vertical directions. So those guys, initially we thought, when we saw X's, we were thinking of St. Andrews crosses, where the group velocity goes in the stratified flow, we have initial gravity waves. Those aren't St. Andrews crosses, those are the critical layers.
So the vortex that we're talking about is induced by instability?
The vortex that I started there was created by me at time t equals 0 in my numerical code, putting in a vortex.
You put a vortex.
I put a vortex there, and it's the almost equilibrium, and it's producing waves, and it's producing these critical layers. Right? Later, I will take that vortex out because astronomers don't like putting an initial vortex into a problem. I'm going to take that out.
So the instability, you can interpret it as resonance?
I can take it as...
Can you interpret the instability as resonance?
As a resonance?
In a wavelength?
No, and I'll come to that. Okay, bear with me on that. That was one of the things we thought
Once
through.
you put WKB...
Bear with me. Okay, so, right, let's solve that. Okay, and I should say, by the way, that there's a lot of energy. Just like in a channel flow and a pipe flow, when you have turbulence, when you have an instability that grows on those things, basically they take that shearing flow and locally, very locally, they take out the shear, they make it like slug flow, which has a much lower energy associated with it. And that's where it's getting its energy from. The ultimate source of energy is that in the capillary of shear.
It's smoothing the shear?
Pardon me?
It's smoothing the shear?
It's right. Locally, it's losing its shear, and it's certainly losing its energy. Okay, so let me go back to the simple plane, get away from the protoplanetary disk, back to our Couette flow with rotation and constant stratification and constant gravity. So Y star was the location of my critical layers. The wave number in the X direction, which I've written as Kx, I'm going to replace that by saying, look, there's some length scale of my domain that's periodic in the streamwise direction. I'll call that L, and then my wave number Kx is simply 2 pi divided by L with an integer multiple m. So that's why there's an m and a 2 pi in the denominator there and an L in the numerator, but that's basically the same formula that I had before. And just to make it much easier to interpret what I'm about to show you, if I choose a unit of length based on that streamwise length L modified by those sigmas and n's, and the unit of time will be 1 over the Brunt-Weissler frequency. In those dimensional units, my location of my critical layer is simply equal to temporal frequency plus or minus 1 divided by an integer m. And by the what does that mean? Location with respect to what? Right? Because there's no boundaries in this flow. What this means, and you'll see it really comes true, is that is if I have a perturbing region, that is the distance between the perturber and the critical layer it excites. That's how this Y star has to be interpreted. It's that distance. Okay. So, if we want to start with a single steady vortex, but for the simplified Boost-Nest flow rather than a protoplanetary disk, the frequency of the disturbance S is equal to 0. And so the location of that should simply be 1 over integer m. So the fundamental critical layer will be 1 unit away from the disturber. The next harmonic will be a half, the next one will be a third, a fourth, and so on. In all cases, though, you're not going to create critical layers more than 1 unit away from where you started. Okay. So here's my plane coed flow shear, and the movies are all on the side. So the movies look like this. You're going to see an unbounded domain. The flow on the far left is going like this. On the far right is going like that. The gravity and rotation are coming out at you. And so here are 4 panels of a movie I'm about to show you. So again, this is my cross-stream direction. This is my streamwise direction. A is a kind of early time. The color represents the vertical component of the vorticity. Green would be undisturbed. Blue would be these anticyclonic guys. Red would be anticyclonic vorticity. And what you see here, critical layer at 1, and it actually starts later than that at 2 and the other ones. He's got kind of one thing here. Here, the m equals 2 critical layer would be located at 1 over 2 or a half. So you see that you get it, and there's both vertical velocity up and down at the critical layer, so you get a kind of dipolar vortex sheet of red and blue. And you see that there's 2 of those because the wave numbers at x n equals 2. And then at 1/3, which corresponds to n equals 3, you see 1, 2, 3 of these guys, and you get this kind of dipolar charge. At later times, we know that vortex layers embedded in shearing flows, with or without stratification and with or without rotation, are linearly unstable, and they break up. Those that have the same sense of rotation as the background shear are unstable. They produce Kelvin-Helmholtz waves. They produce vortices which then merge together, and you get a nice stable vortex, where that's what's going to happen with the blue. The red are linearly stable layers, okay? So this kind of, it's being perturbed, it's not really breaking apart, where the guys are merging with each other. These guys will swallow those guys. These guys will develop later and swallow these guys. And so you're starting to get big vortices. But oops, something's wrong. Notice that I'm getting vortices at values greater than 1 away from my source. My source, you can't see the source here. It's a vortex at the origin, but in the vertical plane, my source is up here, so you can't actually see it. So how can that be? And as you point out, the domain is not only to the right side of 0, it's also to the left side of 0, and it didn't really end over here. It ended about somewhere about maybe a meter past this window. It's a pretty big domain, but I'm only showing part of it here. Okay. Okay, and so the point is that for S equals 0, you shouldn't get any critical layers more than a distance away from your source. But the equations of motion are Galilean invariant. I can always boost into some frame, and the physics should look the same. So after a big vortex is kind of rolled up and swallowed everybody at y equals 1, it's its own perturbation. If I go into the frame that vortex is moving, right, and that frame is S equals 0 type of perturbation, no frequency, it'll excite its own critical layers. And that's what happens. You get a whole cascading of critical layers. And so start here, you excite the first one's over here. This generation grows up, produces its own very large vortices. It excites critical layers at exactly the right locations over here. When these guys become big enough, they excite the guys over here. And it goes on ad nauseum, or ad infinitum, whichever you prefer. The entire fluid is going to fill up with vortices. The vortices will be quite turbulent, as you'll see in later movies. The vorticity of these vortices are, we like to measure vorticity in a dimensionless number. So you take the vorticity and you divide it by the Coriolis parameter. You call it the Rossby number. That Rossby number is about 0.3 for all of these vortices. So those are those are serious disturbances. Those are disturbances on the order of the velocity itself. And so this will fill up everybody with large amplitude vortices that are turbulent. And so that's sort of a later picture. And then because the astronomers like to call this the dead zone, because we created a vortex over here, and it infected the flow over here by exciting its critical layers, and they produce vortices, and then they produce vortices over here. The infection just goes. So we call it zombie vortices for us. In the Phase Lab letter paper, right, we call them baroclinic vortices or something like that. Then we wrote an astrophysical player, so we can't call them that. We call them zombie vortices.
And it passed.
Oh yeah, they love that. Okay. Here's the same thing, except in black and white, which actually shows up a little better. So blue becomes black and red becomes white. This is my cross-stream direction. Again, the actual locations of the calculation are way out here somewhere. And we start with a vortex now, and this is now the vertical direction. So the vertical direction, we put the vortex in arbitrarily at the origin here. The flow is coming out at you here, and the capillary flow is going in over here. So that's our correct flow. And now what you're going to see here is it's very cute. This guy produces inertial gravity waves and shear. And the group velocities look like these curved things. When those group velocities will intersect the locations of the critical layers, they'll excite them, and they'll roll up into vortices. And then these guys, so you're going to get a three-dimensional lattice of three-dimensional vortices will all flow. So that looks like this. So you can see the waves coming up. Here are the critical layers. And so you're going to get a lattice. Now remember, it's kind of blinking at me, because everything's going like this, and it just happens to be in this plane when we snap the picture of it. And so you get a pretty well-structured lattice of turbulent three-dimensional vortices. And one of the reasons these things are so robust is because they're kind of self-organized and self-reinforcing. So here's that last picture. Think of the vortex that's starting at the center. He sends out waves that hit these critical layers. This is the primary critical layer at n equals 1. It was half, which is kind of getting absorbed. So he excites those four vortices around him. We're showing blue. Each of those vortices, right, it's all self-similar, excites four vortices around him, so they hit this guy. Each one of those hits that original vortex 4 times, and they excite these ones. So each ring represents how many times it was hit at that location. So this guy was hit twice. This guy is now going to excite each of these guys excites 4 vortices. So in the next generation, right, third generation, this guy didn't put the rings in. This guy's excited 10 different times. So it really is self-reinforcing, and that's one of the things that makes it such a robust flow. And I'm going to show you an example of that robustness in an unusual way. It came out accidentally, as most of these calculations do.
Can I ask a question?
Sure.
Being hit doesn't necessarily mean being excited. Because it's being hit with a phase and a sign and all sorts of other things.
Well, the whole thing is turbulent, but there's this group energy that's moving energy into that spot. And somehow it's responding to having that energy there in that spot.
Yes, I guess this is very different from vortex pairing.
This is very different from
Vortex pairing.
vortex pairing, yeah.
Classically, it's
Right, it's not like the usual vortex pairing. Right. Okay, so we were interested, there was that S, that was a temporal mode, that was the thing that was exciting. We wondered, maybe we should look and see what happens when S is not equal to 0. So we have wave generators, which are the analog in the laboratory when you want to generate inertial gravity waves in the lab. You produce an oscillator with some frequency, and then you get these St. Andrew crosses of the root velocity coming out, and you get less waves. Okay, so we built our numeric version of exciting something locally with a specific frequency S. And it worked and it didn't work. It gave us a surprise. That's the way to say it. It produced things with a non-zero frequency, but not with the frequency S. And here's why it didn't. So the wave generator was at the origin. Streamwise flows going like this. This is verticals out at you, cross-stream streamwise. What this does is it ends up producing these waves, but the waves themselves from the generator roll up into vortices. So an instant time later, I create two vortices. So my wave generators here, happily putting on the screen, but these two vortices are very robust, and they're just going to go past each other. It's going to go with the flow past each other, and it's got a finite domain size L, so they're happily close encountered. Boom, boom, boom. There's a beating frequency of the two vortices at close encounter. That's a more important frequency in this problem. So what is that frequency? Wait, we've got a length L, streamwise direction. I've got two vortices that are separated in a cross-stream direction by a distance delta, which just happens to be where they're created. And the relative velocity, next as they zip by, is sigma, the shear, times delta. So that produces, we'll have close encounters at some period. The period that they'll have close encounters would be the length of the system in the streamwise direction divided by their velocity, which is sigma delta. But of course, if they go by once, they'll come out again. So really, the period of the close encounter is any integer little p times the big capital P over here. And therefore, we've got a frequency that we're driving the system, not from the original wave generator, but by these vortices going past with frequency that could have an integer associated with it. So there's a whole bunch of frequencies there. Now remember, the critical layers form the wave, they depend upon the wave number kx, which depended upon an integer little m, and 2 pi times the length in the streamwise direction. So if I take that kx, which has its own integer m, and plug it in here, and the frequency s from the last slide, which has its own integer associated with it, of little p, and if I use my unit of length and unit of time as I did before, then I see that my critical layers in this system should be located where? Well, they used to be at 1 over m, and now there's kind of a fine structure splitting. It used to be one critical layer, now becomes a pair of critical layers centered around 1 over m at plus or minus delta, the original distance of things, divided by two integers. So, fine. So, okay, so that's just a repeat of what I said there. So the little tiny distance between the critical layers, one's at plus p over m, one's at minus delta p over m. Therefore, the total separation between this new pair of critical layers is 2 delta over pm. Well, if the new separation were the same as the old separation, I'd have self-similarity and reinforcement. And so, in order to make this guy equal to this guy, product of pm has to be 2. So there's two possibilities, pm equals plus or minus 1, and the two possibilities. All right, the product has to be n equals 2. So we did the experiment. So here's the cross-stream direction, and here is my vertical direction. So this is like the other one I showed you in black and white, except now I'm starting with two vortices. Remember, things are going this way, and let's see what happens when I use this as my initial condition. So it's initially about a separation delta, and they kind of do their thing. They set up, so let's start exciting things that where the new critical layers should be, and it's kind of gloppy for a while. But my argument should be at the integer values, half integer values, and etc. You're not going to see one set of vortices. You'll see two sets of vortices slightly displaced from each other. So here we are. Here's like the m equals minus 2, right? There's no, it's not like this set of vortices on either side of that. In fact, if you go into the calculation, the original vortices were separated in streamwise direction by distance delta. All right. Didn't quite do what I wanted to do. The new guys, the little pairs, are also going to be separated when this thing is done by distance delta. It's going to give you that self-similarity. And nature chose, or the computer chose, or whatever reason chose. I didn't set it up. When it did this, it set it up with an m equals 1. I can measure the m, the wave number associated with each of these vortices, and p turns out to be 2 because I can look at the temporal frequencies. So product is indeed 2, but I don't know whether it's going to be 1 or 2 or 2 or 1 or none of the above, but it's really self-similar as it goes from out. So the self-similar structure is really important for reinforcing those vortices, both here and it will turn out in a protoplanetary disk.
That's a very complicated picture, and I'm not absolutely sure how you're choosing your pairs.
Well, okay, so the 1 over m, the vortices are located at 1 over m, plus or minus. So the 1 over m is 1, 1 over m is a half, 1 over m, okay, so it's these guys here. And then, right, so this distance between here and here, that is my delta over pm. Okay, so the separation that I've written, between the midpoint between these pair, the midpoint between these pair, the midpoint between these pair is basically 1 over m. And the distance away is plus or minus that other distance. So what I'm saying is that right, where there isn't a vortex, but kind of sandwiched between two pair, is located indeed at 1 over m. And then a distance capital delta to the right and capital delta to the left divided by pm, there's another pair. And that pm is equal to 2, the product's equal to 2. By analyzing the flow, you can see that p turned out to be 2 and m turned out to be 1. Okay, so all of this is great, but when I gave this talk to the astronomers, they gave me a hard time. They said, well, they gave me a hard time for a number of reasons. So let me just explain the last few minutes what those reasons were. But the main thing they said was, you cheated. You put a vortex in at the origin. No, that's not acceptable. Right? To do an astrophysical calculation, it has to be noise. It can't be a vortex. It has to be incoherent noise, and it has to be common R noise. Okay, fine. And it's not like at time t equals 0 in the Big Bang. There was a Keplerian disk, and there was noise. Right? The thing came from the collapse of a big core. But we're looking at that. We're going to play by the games of the astronomers and see what noise is. But I absolutely knew that they handed me a softball. I should also say, in order to get this published, I delayed publication because I wanted to meet all the conditions. Right? If you're coming from a group, you're not really a member of that group. You got to play by the rules, right? Okay. So,
can I ask a question?
Yeah.
Which is, you're telling us it comes from collapse of something, and that collapse of thing would very well have angular momentum. In fact, it probably doesn't have zero angular momentum.
Right. That's what made the Keplerian disk. The angular momentum is preserved to make the Keplerian disk.
Right.
So, and you can watch these calculations. People have crudely gone down.
So why should you put in zero angular momentum, total angular momentum?
Well,
come over.
Wait. I'm playing, like I said, by variables. But there are some things to be learned there. Okay, so let me say that. Okay. First of all, the other condition was that we used a spectral code, or sometimes use a spectral code in some cases. We use a pseudospectral code, which are really nice because you get a lot of resolution. There's no dissipation unless you put it in explicitly. They said, no, you have to reproduce this with a first-order finite difference code.
Oh, come on.
No, that's the rule, right? So there's one which I put a theme that everybody loved. So we ran it with a theme. It's fully compressible. We reproduced the results. The difference is that a theme, because it's a finite difference code, if you have a certain number of resolution elements, but if you have n resolution elements for a spectral code, you need roughly in each direction 4 pi n to get the same resolution. So we did this with the most under-resolved Athena version we could get away with. And also, for even for the same number of resolution elements, finite difference points versus spectral modes, the Athena code ran 140 times slower. So basically, used up our entire computer budget. But they're very happy. They're happy. I'm happy. Okay. So noise. Okay. One of the things, right, for finite amplitude instability, how do you tell what a finite amplitude is, right? These days they require a kick. They require an additional vortex or something. Now we're going to try and kick it with noise. Well, one of the things we discovered, just by varying initial conditions, is that many finite amplitude instabilities, there's a threshold velocity you've got to get above, or a threshold energy you've got to get above, or astronomers would say a threshold Mach number, you take the velocity divided by the sound speed. But the thing is, astronomers say, I apologize, I love astronomers. Okay, but we discovered this was not determined by velocity. It was determined by a critical amplitude of vorticity. Vorticity is different than velocity. It's got another length of velocity. Okay. And that's what makes all the difference, which makes it so beautiful for noise to kick off, right? You've got the energy spectrum, right? Energy is a differential energy spectrum. It's a function of wave number k. You get k to some index, k to minus x. So a is my index of my noise here. Of course, if you want to think of an eddy, eddy's made up of an integral of wave numbers around some known value. So the RMS velocity of an eddy with wave number k would then go as k to the 1 minus a divided by 2. And if I think of the RMS, if I think of 2 pi over the diameter of my eddy L in wave number, then the RMS velocity of an eddy of length L will go as, if capital is my largest length in town, it'll go as little L over L with some power over there. the vorticity will scale differently. Right? The vorticity is divided by the velocity, so in wave number space, the RMS velocity of an eddy versus this power, the RMS velocity is a function of length versus this power. All right, so for values of A, between A and 3, the velocity is all the largest scales eddies, and the vorticity is all in the smallest scales eddy. And of course, 5/3 is in between. So for Kolmogorov spectrum, the vorticity is at the smallest length scale, and that's why these guys handed me a softball. Right? If I were to plot as an initial condition an energy spectrum that's completely incoherent, it has a k to the minus 5 spectrum. If I plot the velocity in some plane, it looks like that. It's all the largest scales where it is, and the vorticity is all the smallest scales. That's the pixelation size of the calculation. On the other hand, if I take k to the minus 5, both the energy, the velocity, and the vorticity are the largest scales. Okay, so there's a big difference in these things. Okay, so this is a complicated picture. I'm trying to explain it in the next couple of minutes. What we did was we started with Kolmogorov noise. And of course, the whole thing went crazy with zombie vortices and turbulence. And so we lowered the energy of that spectrum. And here is a plot of typical log-log plot. Here's the wave number. So here's large wave number, small lengths, big lengths over here. Here's a plot of the Rossby number. I took the vorticity in the vertical direction for that wave number and divided it by the Cordell's parameter. And so this black line over here is basically my Kolmogorov. And it turns out we had kind of discovered that the critical Rossby number, vorticity, to make this thing go crazy and produce all this turbulence was that red line that's over there. So there's also a resolution on this. We don't go to infinite wave numbers. We have some sort of resolution. So the solid black curve, which goes up to this resolution, the highest point of that, which because the spectral index is always on the right side, is below the critical value. So that just, you put it in, nothing happens. Okay, and then we increased the amplitude in front of the k to the minus 5/3 coefficient. We parallel transported this line over here to this dashed line, and it peaks above, and it filled the whole thing with crazy turbulence. Then we tried another experiment. We started off with the energy of the thing in the black line, but just changed the index, keeping the total energy and therefore the velocities at the large scale state. Which changes the angle, you got this dotted line, and this guy became turbulent, and as you change the angle when the rightmost point went below that line, it stopped being turbulent. It just didn't put large turbulence. But then we did something else. All right, we took the k to the minus 5/3 with the energy coefficient in front of it for this resolution calculation, which it didn't get above that red line, and we said, heck, let's give it more resolution. So the calculation stopped here, and of course the edge, that black link, is above it. And it went turbulent. So the point is that when you have a protoplanetary disk with effectively no viscosity and huge length scales, you've got a huge Reynolds number, right? So if you go down to the Kolmogorov length scale, if that's the guy, that's going to be, back in California somewhere over here.
That's
right?
east.
And so you can start off with minuscule amounts of energy or velocity, and you'll still be above the red line. So in fact, you do the calculation, and you can show that basically the Mach number, the velocity divided by the speed of sound, to go unstable, is basically 1 over the square root of the Reynolds number. And a typical Reynolds number that people talk about for turbulence is 10 to the 12th. So the Mach number is 10 to the minus 6. So yes, it's not a linear instability, but it sure doesn't need much finite magnitude. Okay, so I better stop there. So let me sort of skip through the various things. Oh, this should end with a picture.
You have time.
I have to stop.
It's 5 minutes or 3. I mean, it depends on how much one you want to say.
Okay, all right. Well, okay. So this is a picture of turbulence where it's just below that red line. And basically the shear stretching everything out, everything is dissipating like crazy, and nothing interesting happens here. On the other side is where we're just hoping. Pardon me? That was a movie, but it's all decaying, so you can't see it. Here's the one. The shear is stretching everything out, but there's a little bit of inverse cascade because it's a stratified rotating system. And you produce little isolated vortices, effectively. And once those vortices get their sufficiently big Rossby numbers, right, they're going to make this thing go unstable, and it happens pretty dramatically when it starts to go. So you can see the vortices are inverse. Now it's exciting critical layers. Now the whole thing is going to fill. This is in the vertical cross-train direction. Those are vortices. The blue anticyclonic vortices form very turbulent vortices, right? And the red is cyclonic vorticity. That tends to form sheets between them. So there's clearly structure here, but the whole thing is very turbulent. The whole thing has Mach numbers, which are the same as the Rossby numbers when you go to a fully compressible calculation, and about 0.3. And that is enough to do all the things that astronomers want you to do. If these things launch acoustic waves, the acoustic waves are very efficient in transporting angular momentum and will make a star. These things are also very efficient. Well, we don't know. We know that vortices that laminar are efficient in attracting particles and can make planetesimals. But we don't know of turbulent vortices, so that's something that we're looking at right now. The other thing is that it really tells me that the flow inside these disks is not laminar and capillary. It's highly turbulent, highly mixed. The leftover junk from making stars and planets, that junk is meteorites. We have a lot of meteorites. Inside many meteorites, we have these things called chondrules, which are kind of centimeter-sized marbles. And you can look at those, study those guys, and they show that they could have not have formed in a laminar disk. They have visited basically large sections of the disk in radius. They're very well mixed. You have to have turbulence to do that. So we're hoping this will also explain observations of meteorites. In another direction completely, we're looking at the structure of the critical layers themselves, trying to understand, as a function of mixing Reynolds number and diffusivity and also nonlinearity, what the scaling of the thickness of the critical layers is. That's important from both a theoretical point of view and from trying to compute these things to tell you what the resolution that you need is, but also because we want to build these in the lab. It's possible that when the James Webb Telescope is launched in 3 years, which will be looking at infrared, it's very good at measuring the emissions of dust, better than the Hubble pictures, that you'll see something that's a signature of these guys. But we want to try and build these in a laboratory. So I'll stop and thank you and take any questions.
How do you do it in the lab?
There's 2 ways to do it in the lab. One is you can do it in circular Couette flow. You don't have constant shear, right? You do it in salt water, but you do it rotation. The other is you can do it in a box or a rotating table with a plain Couette set of bolts.
Yeah.
And so, Patrice Ledal and Kevin Barr down in Marseille are working on this now, and we're trying to find the sweet spot numerically of. We can change those 3 time-like parameters: Coriolis parameter, shear, and bicycle frequency. We're looking for the values of those that would produce this instability at the least expense for the people in the lab. So that's what
those would all be incompressible.
Pardon me?
Those all be
Maybe on Boussinesq, right. But the thing was originally discovered in Boussinesq, and the Boussinesq is just fine for this. Everything else just makes things more complicated than this.
I have a naive question, because you gave us 2 sets of coordinates, and I'm confused. Just tell us what coordinates.
Okay, so this is the cross-stream direction, which would be like a radial distance from the star. And this is the vertical direction along the axis of rotation and gravity. I can show you the movie.
So if you look down on that picture on the right, you see spots that are being sheared.
Right. No, not this one. Right. So the other plane, right? The shear's coming in and out of the board.
Yeah. Okay. But look at it.
Oh yeah. Then you would see it. Then you would see the arc.
So those blue lines are sort of the centers of the long spot.
So yeah. So the board. So this. I'll put this picture. This is. If you look at it in the other direction, it's very similar. By the way, that was for the anelastic, not Boussinesq. If you look at it in the other direction, this is the. So if you look at it in the streamwise direction is now this way, the cross-stream direction is now this way. That's when you got these things. Right? But that's from a single. In turbulence, you start with turbulence. It's going to end up. The end states are going to look almost the same. So here you see that it looks kind of more coherent. It looks less turbulent this way. But the red's kind of cyclonic things tend to fill sheets, and the blue things tend to fill vortices.
And the vortices have low pressures in the middle?
Oh, okay, so the anticyclones have high pressures in the center, and these cyclonic sheets have low. And it's the anticyclones that will centrifuge in heavy objects. So that's good for making we know if these were laminar, they would suck in grains like crazy. We don't know how they do in a turbulent vortices themselves.
I always heard that it was the inelastic collisions of the random chuck that.
Well, okay, so actually having grains collide is not a good way to try and get them to accumulate.
That's because of the density that you mentioned.
Well, okay, so if you want to have interaction grain, so there's two things. What's the fluid do? Let's see, black fluid. Let's see, math. Let's see. Now, how do I turn on the lights?
Yeah, that's the light.
So the idea is I've got a vortex and it's got a high pressure center here, right? So the pressure is kind of decreasing as I go out. Right? It's balanced by the Coriolis force. So now I'm going to take a little parcel of fluid here, and I am going to replace that parcel with a something that is massive. Okay? So before I did the replacement, right, the balance of this parcel was the pressure forces on this guy over here, which are trying to, there are high pressures over here and there are low pressures over here that's trying to push it out. And that's being balanced by the Coriolis force, which is, or I should say acceleration, trying to push it inward. Okay. So the point is that one of these has the Coriolis force and the pressure. One has a mass in it and the other doesn't have a mass in it. So when I replace this volume of fluid, the force that doesn't have a mass in it doesn't change, but the force that has a mass in it or a density in it does change. Right? So if I have gradient P over rho equals F cross V, and I multiply both sides by rho, it's the Coriolis force that has the mass. So that's the one that is going to, if I increase the density, by replacing the water with a massive particle, that's the one that's going to be important. And so that's the Coriolis force which is pushing it in. That will win over the pressure. So that's why if you replace a parcel of fluid with something with higher density, it will go into the high pressure center. Okay. So particles are attracted that way. What gets them to actually interact with each other and accumulate is you've got to start having collisions with particles. But long before you have collisions with particles, okay, so I've got a particle here and a particle here. The chance of these guys hitting each other is not good. But when a particle goes through, it produces a weight deficit of momentum. This guy's going to cross that. Right? This is a much bigger target than him himself, right? So he crosses him, and then once he gets in the wake, they start interacting with each other. That's the way these guys really do. The original attraction is due to this effect, and then the next piece of attraction is due to this effect. Yeah.
Many people asked before about how the vortex sheets relate, stretching into the
So okay, so once so the critical layers get things started, and these things, but once it becomes turbulent, right? None of these guys are going to hang around their linearly created critical layers. But the point is the imprint of the critical layer spacing remains on these guys. So if I look at it, well, there's 1, 2, 3. 4, 5, 6, 7. Right? Basically, if I look at these guys over here, then the separation, if I average the separation between the red sheets here, that's going to give me my critical layer separation distance. It remembers that. If I have a disk, back to the protoplanetary disk, so that's the midplane of the disk, then because the Weissler frequency is basically linear in the distance from the critical layers kind of look like this. And so the separation between the critical layers changes as a function of height. And early on, as you saw on that slide, you see that. But when vortex sheets start being produced and rolling up, they happen most quickly about 1 pressure scale height away from the disk. Because, in fact, that's the height where the Weissler frequency matches the Coriolis parameter. That's where things happen fastest. And as things become nonlinear, everything eventually gets this space. This guy's lowest. That's a linear thing, and the nonlinear remnant of that is it remembers the spacing between the critical layers where it's starting to grow the fastest. That just takes over the system. Were there any astronomers here, Bob? You must have a lot of criticisms.
Well, I want to try to relate it to some of the problems that the MRI and turbulence was leading to this. So, are zombie vortices capable of transporting angular momentum radially?
Good question.
Quantify.
Okay, so let me answer that for you, and I'll tell you what we're doing now. Okay, so if here is a star, okay, and I produce a vortex around that. Most vortices, especially if they're around there, are front back symmetric. So this guy's going around the disk, okay. But if I were to draw a line, I would bisect it this way. These guys are nearly symmetric. So the component of velocity there has the same component in this direction as this guy, but this guy's going up that way there. Okay. The angular momentum transport, let me Cartesianize things. So this is x and this is y. Right? Depends upon the correlation of the vx and the vy component of velocity, right? Okay. Well, if this is symmetric, this vortex isn't going to do anything. It doesn't. On the other hand, if you have a field of vortices all around, as they go by, they really oscillate each other. And this point turns out not to be zero. And it gives you, in your language, an alpha. Okay? But it's too small now. It's about 10 to the minus 5. And so first we were excited about that, then we realized that's not going to work. But what we did discover is the following. So if you, we couldn't afford to go all the way with the Athena code or any compressible code that we had written because it's too slow. But the anelastic code, right, it filters out all the sound waves. So I can write any velocity field as a component that has a divergence but no curl, and two components that have no, their divergences, one's colloidal and one's toroidal. And so when people do a lot of experiments, if you take a flow and you force it, one of those three components, if it becomes certain, you get equipartition. Okay? If we're betting, and the early calculations showed that if you, this is purely producing rotational components, colloidal and toroidal. We're betting that it comes to, it also equilibrates, and that the solenoidal part, the part with acoustic waves, will have the same kinds of Mach numbers. If it does, acoustic waves are great because for the correlation, right, Vx, Vy for sound waves, then is Vx, Vy, so they're completely correlated. So sound waves, acoustic waves are the thing that we want to excite. So we're looking to see how efficient this is at first equipartitioning and then producing sound waves, because your alpha would be then be equal to, so if I write this as a correlation constant there, it would be the correlation constant here times the Mach number squared times the fill factor, what percentage of the flow is filled with turbulence. This number always turns out to be about 0.3. The Mach numbers are always the velocity numbers, so draw 6.3, so that's 0.3 squared. Correlations of order unity. That's a big enough alpha in the stars. We're testing that now numerically, but we can't really test it until we get our efficient spectral code that can handle the Mach numbers up to about 3. We don't expect any Mach numbers of about 0.3, but we want to make sure that we really do the acoustic waves right, because that's going to transport them. Okay, thanks.
Any further questions? Thanks very much. I think there's tea for us.